Hello everyone, welcome back to my channel, Black Box Engineering. So I'm gonna kind of start up a a playlist of different LTSpice things because I think that it could be good information to use. This program is very powerful, but it can be a little bit clunky to get to learn. So this very first one, I'm going to be showing you how to set up a test circuit to emulate the idea of transistor characteristics. For those who aren't familiar, it is a graph that typically represents how a transistor reacts to input current on the base. Let me just throw in a transistor here, an NPN. We're going to be focusing on NPN. So based on the input current through the base here, we can analyze how the collector current is going to increase based off of what's known as the beta factor, or the multiplication factor of the transistor in question. So let me just grab a random graph here online just to kind of show you. Without context, it's kind of hard to explain. This is on a website called Electrical Academia. Let me just get a close-up here. So we compare the voltage of the current emitter. So that's the this is the collector emitter. So this is the collector, this is the emitter. So we're comparing the voltage of the between here and here, and we're graphing it against the input current on the collector, which is going to be the current through the leg here, and it depends on the current that is present at the base as well. But we graph these two measurements in reference to each other for how transistors behave. The reason that this is important is we need to know kind of where a transistor is going to act as an ideal switch or as an amplifier. In this case, right about here, this, if you can imagine a vertical line, right about here, beyond about 2 volts on this particular transistor, it pretty much seems that any current up to 120 microamp on the base will reach the saturation of the transistor. And to the left of the line is called the inactive region, and this is where transistors behave best as amplifiers, I believe. And then of course at 0 you're going to have a cutoff region where it's not going to work at all. So you can actually kind of copy this through LTSpice to kind of test out a bunch of different transistors. So like if I wanted to, I could literally go through a list of, as long as it has a beta factor right here, you can kind of see how each one is going to react, and they're not always going to be 100% consistent even if they have the same beta factor, because there's a lot more parameters that goes into a transistor, obviously, as you can see by the list. But mostly we care about the BF when it comes to transistors. So what we have to do is make a test circuit for this. So I have a test circuit set up on my other screen here, so I know how to set this up. To get components on the screen, by the way, you just click this little thing here that says component, and then you search for what you need. In this case, we need an NPN transistor, and let's just say that we want to use the 2N2222 transistor for now. And then we need a current source So CUR. And technically, as I've mentioned before, this doesn't really have an equivalent in the real world. This it's just a little bit easier to set up the example this way. And by the way, the reason I'm not showing my face right now, I have a bloody nose and I don't want to have my tissue on screen. So anyway, so we need a resistor in series with the base. So I usually like to have a voltage divider actually. It just makes it a little bit more consistent in my opinion. So I'm going to just hook that up to the base here, and I'm going to make this 200K and 100K. The reason I go for such a large resistance is you don't have much of a drop in voltage, so the current will basically be the same on both sides, which is important for how we want to test the transistor here. Then I need to hook up a ground point here to the emitter, and then I need a voltage source. So VOL, and for now I'm just gonna type 16, but we're gonna actually change this in our running, our simulation run. You'll see what I mean in a second. And then we need another resistor, and I'm going to use a value of 50 because I found out if you go too high, you will end up needing way more source voltage to overcome this resistor in series. I had it at 1,000 before, and I was like reaching 80 volts to reach saturation, and that's not normal. So this will make the current higher and the voltage lower for the actual between the collector and the emitter. So from this, I need to draw a node here to make sure I know what so you can see what's going on. So from here, collector to emitter, we just need it to be not so dang high, because that's not how we typically see. That's not how we usually test transistor. How people test transistors. So what I'm doing here is I'm adding a voltage node here, just to label the voltage output. Technically, the collector emitter on this side would be the quote-unquote output voltage point. So yeah, so this is all that we need for the circuit, and now we have to add the running the spice command for the run, the simulation in itself. But before I do that real quick, the beta factor for this particular transistor is 200. So we can just pick different ones to show you the changes as we go. So we need to hit this little running guy here, and then we need to switch to DC sweep. The first source we're going to sweep is the current, so I1. It needs to be linear. The start value, let's say 0. And let's say we want the stop value to be 1 milliamp. In this case, we want our increment to be like definite steps. So imagine like 100 microamp, 200 microamp, 300 microamp, because that's what we saw in the actual graph. So I'm gonna use 100 microamp steps. And the second source we need to sweep is the voltage over here, the V1. So V1, it needs to be linear. The starting voltage needs, let's say 0, I guess, and let's go up to, I guess, 16 volts. And in this case, don't We don't really need an increment, but just to be safe, we can just make this small. Not stepping the voltage in like small, like big, or I should say big steps. So we can actually make this pretty small. I'm gonna say, I don't know, 10 milli. And then as we see, this ran. So if I probe this current right here, we're gonna get, oh, that's actually way too much. Wait, hold on. Oh, that's way too many steps here. Okay, I definitely goofed that up. Let's see. Let's try 500 microamp. Okay, maybe my step is way too small for... Let's just do 1. That looks a little bit more normal. It's still a little bit too... Hold on here. Let's see. Oh, oops! I'm mixing up the order of this on what I'm stepping here. Okay, so that actually matters in the simulation. Okay, so I gotta fix that. So we actually want to switch order here. Let's say V1 is the first thing that we're gonna step, and we're gonna go to 16 volts, and let's just increment in 0.1 step, 0.1 steps. Come on, 0.1. Second source should be I1. I had that backwards. We're going to start at 0. We're going to go in up to 1 milli. And let's use 50 micro, 100 micro. There we go. That looks a little bit better. So, as we can see, this looks pretty much like what we had before in the actual the web page. So, what we can gather from this is, given this setup for the transistor, it looks like the active region up to approximately 135 milliamps is about 7.2 volts between the collector and emitter, which makes sense for the components that we have in place. Another cool thing that you can do is you can actually graph like the beta factor and all that. I just need to reference the equations really quick. Give me a second here. It's been a while since I've done this, so since beta also equals the collector current over the base current, we can actually graph that by doing a little bit of trace math. I'll show you what that means really quick here. So in LTSpice, you can actually add like equations by right-clicking the graph here, add a trace, and it'll list a bunch of different available like currents and whatnot. So if we take the collector current and we divide it by the base current, we should get very close to the what was it, 200, I think, 200 beta factor. Granted, it's not going to be, so in engineering world, we're supposed to think of beta as being a constant. Technically speaking, it's not going to be 100% like always 200, but it's better to just calculate everything as if it were 200. As you can tell, if I just zoom in here, the lowest it is, and this is based off of the highest value here, because on the other graph, hold on, I just got to go back here. So if I go back, you see how it's increasing. The very last step is going to be the final beta. So just gotta IC over IB, and I can delete this trace. So yeah, so this is from left to right, it's going to be the lowest current, which typically makes sense. It's going to be closer to that 200 value. And as you can see, it does slightly increase once it reaches like the active region here. So yeah, the beta kind of before active region, it shoots up linearly, but it doesn't level off until it reaches that saturation, and that's how the characteristics work in a transistor. So anyway, all I'm trying to say is that for all intents and purposes, this is considered 200, even though realistically speaking, it might be best to kind of test your transistor to see if it's actually holding at 200, at least to get 100% accurate data for calculations. In this instance, it really depends on the VCE, really. So in this case, for the least amount of current, we're going to be looking at approximately 7.8 volts, and then for the most amount of current, it might not ever reach 200 actually. These regions do not converge very quickly. They're pretty much level. If I went to, like, I don't know, let's say 35 volts, just as an example here. Yeah, so as you can tell, it takes a very, very long time for these to increase, and the in reality, the 2N222. Let's see here. So let's go to digikey.com and see if this. See what this says, well, at least for on semi conductor. So the collector emitter breakdown maximum voltage is 30. So realistically speaking, around 30 volts, you're pushing the limits, and then once it goes past 30, you're basically burning out the transistor. So it's best to just assume a beta of the 200, but you might want to actually test things like this so that you can figure out a pretty consistent beta for your particular current emitter voltage. I'd say for the highest current, it's going to be anywhere, I'd say it's about, let me change the tick distance here so I can kind of see a little bit closer here. I'd say about 140 to 170, so like the average, which would be 170 plus 140 divided by 2. If I put parentheses in the right spot, then I get the right answer. 155. So yeah, 155 would be more accurate for this region right here, and it'll be much closer to 200 at the very minimum current, which is, hold on here. This is one thing I don't super enjoy about LTSpice is windows get a bit funky. The minimum input current is, well, besides 0, 0.1 milliamps. You're going to get approximately 20 milliamps of output up the collector current, because beta, you take the 200 times the 0.1 milliamps and then you get the, that's how that math turns out. So yeah, kind of an interesting process there. Technically you can even plot something called alpha, but all it ends up really being is 0.99 most of the time. So yeah, so this is very useful information, and it gives a more realistic view of how the graph would look in like a teacher's drawing. Their y-axis is far more, I guess you could say, logarithmic, because, well, like if I switch to log, well, it's going to mess up the spacing of the rest, but you see that they're a lot more steep in someone's like drawing, like approximation, I guess you could say. Oops. In reality, it slopes off, kind of follows this general curve when it starts conducting. You can actually kind of see this happen. See, at the first current, it won't start conducting until it hits saturation, and then it follows the current of the of this side, and then it just increases and increases until it hits saturation. And yeah, so this is a good way to test different transistors. Of course, this transistor is obsolete, but let's say if you wanted just a final quick example here, let's try finding a beta factor that's a little bit lower. So I'm gonna just kind of shuffle around in here. Okay, so this one from NXP has a beta factor of 78. So if I switch this over, hit run, this will look pretty much the same. But the thing is, when I do the the current values are going to be a little bit different because the beta factor is going to be different. So I just mean that the overall look of it's going to be the same, because it's the same graph appearance will always be the case, because that's how the trends work. So if I were to do the IC over IB, we can actually see that the beta should be, or the lines should be close to the 78.32. So let's just do that really quick, and then I'll end the episode here. So I'm just going to delete this, add trace, IC over IB, and let me just make sure, 78.32, 70, yeah, that checks out. So yeah, pretty good information to go off of if you wanted to know how to do that in simulation. So yeah, thanks for watching, and I'll see you in the next one.